Hey, so we're doing some quantum office hours. And we were talking about the repeat 4 points back quiz, and people were asking about the particle on a ring model. So we're looking at benzene. The idea here is there's two things we talked about already that I'm just going to go over again, so it's recorded as well. When we're thinking about what kind of particle is traveling around this ring, the quiz that I graded already had people doing carbon atoms, it had people doing protons, it had some people doing electrons. And when we think, okay, well, if we're looking at this, what's actually going to be traveling around the ring? It's going to be electrons traveling around the ring, right? The carbon atoms are fixed in the structure, and that is what makes the ring. And then the electron is going to be traveling through that pi system. The other thing that came up is whether we can just use the bond length as the radius, or if we have to do some other math. I will give credit either way. And the reason is because if you look at the circumference, it's going to be essentially 6 bond lengths. So 1.3, was 1.3 the bond length or 1.39?
1.39.
So you're going to have 1.39 times 6 to get your circumference. And then your circumference is 2 pi r. 2 pi is approximately 6. It's 6.28, 6.3. So technically, it will be a little bit different than 1.39. But I'll give credit for either one. You don't have to solve for the exact radius. It'll be close enough. For the like this is already pretty approximate, so it'll be close enough. Do we have other things we want to discuss about number 4?
The energy levels, like what the drawing you want that to look like.
Okay, should I just show you? So let's do some thinking about. I didn't need to erase that to do that thinking. So let's do some thinking about what energy levels are possible. And we'll take a look at that. First off, did you all notice that this problem was directly in the textbook?
Yes. Yeah.
So when we think about this, our energy for the different m sub l's is given on the equation sheet. And that's going to be m sub l squared. Is it h bar squared over 2i?
Yeah.
Right, so we can essentially say this is going to be m sub l squared times some constant, right? H bar squared 2i for our system is going to be some constant. So what possible m sub l values do we have?
0 to 3. 1 to 3. -1.
There we go.
I did not
Right,
do that.
it was the, so like, right, m sub l, and then we could keep going, right? We could go 4, 5, 6, 7, 8, 9, 10, keep going. I only wanted you to do from 0 to 3, and you notice I did absolute value of 3 because it could be plus or minus. So when we calculate our energy, energy of 0, most people got this one right. It's just equal to 0. So if we wanted to draw a diagram for that, where that was on some like energy diagram, we'd have one value at 0. Then, if we did our energy for 1, that's going to be 1 squared times a constant. And we'd end up with, one line. What if we did it for E minus 1? Right? Since this is going to be plus or minus squared, we're going to end up with 2 energy levels there. And then you can just keep going.
So because we're only doing the positives because it's absolute value, it is just the ones stacked up?
Well, no, because it is plus or minus 1, so you end up with 2 lines possible.
But because on the quiz you only ask for the absolute value, so it's the positive and the
Well, the absolute value could be positive or negative.
And then the energy is just like up to scale, like according to the number you got.
Yeah. And the energy. Come on in. If you don't mind sitting on the floor, you can scooch in here. Let's get bags like under desks and under chairs so there's space for everyone to come in. Right, so in this situation, since the epsilon L value, since it's the absolute value of 3, it could be positive 3 or negative 3. That would still give us 3. Question back over there.
All 3, like, positive plus minus 1, plus minus 2, plus minus 3, because there's that double, like, degeneracy.
Yeah.
And those 3 levels will have, because you're looking at the absolute value, each one will have 2.
Yep.
Okay.
And that's where in the problem I specifically said with degeneracy. Question here.
So then would we need to put in the electrons too with the arrows?
Yes.
Okay.
I'm not going to do that part. So that's for part C, which is how do you fill in the electrons to figure out which one is lowest occupied, which one is the highest unoccupied. Yeah.
Okay.
I just don't want to do the whole thing for me. But yeah, it's just.
So you made a comment about the degeneracy.
Mhm.
How do we account for that?
So the word degenerate means two energy levels with the same energy.
Okay.
Right? So if you calculated this E1,
Let's say it's like
You-
2 or something.
yeah,
so
let's say
it's
this, right, you can't tell if it's the +1 state or the -1 state because those would have the same energy since it's m sub L squared. And so that's degeneracy. We end up with situations when we were calculating the hydrogen atom energies, only the N value, so this is not related to the quiz, this is just the idea of degeneracy, so I'll do a little aside over here. When we were calculating our N values, N equals 1, N equals 2, right? Right, since nothing we did up to that first point, nothing we did up to that first point made a change in the energy besides the N value, N equals 1 had no degeneracy. N equals 2 ended up with 1, 2, 3, 4 degenerate states. N equals 3 ended up with 9 degenerate states. Right? 9 states where we couldn't tell the difference between the energies.
Mm-hmm.
With what we did last time, we were like, oh, if we put more than one electron in there. With one electron for hydrogen atoms, that's true. If you have more than one electron in there, we see the spin, we see that total orbital angular momentum, the orbital-orbital coupling, the spin-spin coupling, and the spin-orbital coupling. And that's going to make it so those energy levels are no longer degenerate. They're actually going to have splits in their energies. And that's what we were getting to with the term symbols.
And then, I'm sorry, I'm asking a lot of questions.
No, that's okay.
So for the difference of energy levels, since there's 2, like, in the second level, we would just add that up and then, like, add the other ones and just subtract it like that? Or would we... Like,
When you say add it up.
I mean, like, those two, like...
Just take the difference between E1 and E2.
So, like, would E1 be equal to, like, let's say we get 2, so it'll be 2 plus 2, because there's 2 of them?
No.
Oh, is it just...
No, so it's just the energy of this level. Any electron in this level is going to have that energy. And then if we're moving one electron up, any electron moved up is going to have that energy.
Okay.
Now, if we were asking something about total energy of all the electrons, maybe we'd do something where we add them all up, but we don't often ask for that. We usually ask for just transitions of single electrons.
Okay.
So for the difference in energy, you just want it in between the levels.
Yep. So I tried to make problem 4 a little bit more of a simple walkthrough than what the textbook did. So it was like, just do this step. If you can do that right, that's okay. Like, you know, if you look at part A, it's like, okay, just calculate, just plug in all the values here. And then part B is like, oh, just take the difference between your values. And then part C is like, oh, you just have to figure out highest occupied, just pick the right value out of the ones you calculated. Rather than just doing it as, because originally the problem was just the first line of like, tell me what the delta E in wavelength is for benzene. And that's how the textbook does it. So I tried to break it into like 3 distinct steps, where each step by itself isn't that difficult, but all together we're describing something that's kind of interesting. Other questions? We'll stick with the makeup quiz first. And then we'll go to other questions. 2A. Let me take a look at that
No,
real quick.
actually 2B. I think I got 2A down.
Okay. So let's look at, so this is showing whether a function is still an eigenfunction of L squared. Right, so I'm not going to do it for L squared, but we can look at something like LZ, like what we did on the worksheet as comparison, and see how similar / not similar this is. And I'll do it for something different. And again, I'm not going to say if this is the same. I think because I'm going to make up something a little bit random right now, it's going to be different than the makeup, but it's going to have a similar effect. So let's show. I'm just going to change it. determine, let's do determine. Because I don't know, since this one is not, I'm not sure about this one. So we're just going to determine if that's psi. I'm going to do it for the same function. I wasn't planning on doing this before, but this seems like more fun. So we're going to use that function that I have written down on the makeup quiz, and I'm just going to apply LZ to it and see what happens. So I'm going to have LZ operating on y20 plus y21 plus y2 minus 1. And I can already tell I'm going to have a problem here. I don't think this is going to be an eigenfunction, but let's see what happens. So if I apply LZ, so I'm going to distribute this operator to all three, and we're going to have LZ operating on y20 plus LZ operating on y21 plus LZ operating on y2 minus 1. Where in order to make this easy, right, rather than writing down this as like I h bar d by d phi on whatever function this is, I can just remember that LZ operating on some YL m sub L is equal to h bar m sub L y of L m sub L. I know the individual spherical harmonics. Better?
Yeah.
I know the individual spherical harmonics are eigenfunctions of LZ. So notice, instead of applying this to like this additive function, I'm applying the operator to each piece of the function. I don't know how it's going to operate on each of these pieces. The question becomes, do I get the same function back, or does this mess things up? Well, I can already tell this is going to mess things up, because what's m sub L for this function? I'm going to have 0 times y of 20. Technically h bar times 0 of y20, plus h bar times 1 of y21, plus h bar times negative 1 of y2 minus 1. Hey.
Oh, sorry.
So in this situation, right away, I can see that I'm going to get h bar times y21 minus y2 minus 1 I don't get my same function back. So in this situation, if I asked the question, if I changed the question slightly on the assignment and said, hey, is this an eigenfunction of LZ? The answer would be no. Because when I operate LZ on the function, I get a weird different function back. Technically, it's a rotation of the function, but we're not going to get into that. Right? This ends up looking like, so that was like a dz orbital. This ends up looking like a dxy orbital. But that wasn't the point. The point is, it's not the same function. Something has changed. Question?
I just want to make sure that I have the L squared correctly in my notes. What is the L squared?
So, did everyone fix the typo on the equation sheets that I handed out at the beginning of the quarter?
Yes.
Right, so L squared on y of L m sub L should be equal to h bar squared times L plus 1 YL m sub L. Now, on the equation sheet, it had an equation where it was talking about not the operator. It was just like, if you wanted to talk about this L squared magnitude, it had it equal to the square root of L times L plus 1 h bar. And the equation sheet was originally missing that square root over the L squared.
I thought that the square root wasn't there.
Okay.
Because I went back, I found the McDonald video, and she had it as just L squared without the
She
square
had it
root.
as L squared equals square root
Mhm.
equals to the square root.
And like doing the Like some
This
of the
was-
problems, it was using just L squared.
Yeah, that's why I was confused, because I was doing both problems and it just had L squared.
So maybe it's not, was it not a typo? L squared, so L squared, because the L squared operator is equal to that, yeah?
Yeah.
Am I messing up something in the definition of how are they defining L without the operation then? Because I would define L without the operation. And I looked for this in the textbook and I couldn't find some place where they had it in our textbook. Okay. So here, okay. Okay. So there's a particular way that it's written down in the textbook. Okay, so I think this is just a difference in notation. I have to be careful about this. The vector length is L times L plus 1 to this 1/2. So the way that the book has this written down is they don't call it L squared. They just have the word magnitude. They just have magnitude is equal to that. And so when I think of the magnitude, I think of absolute value of L, like the length of your L vector, which would be the square root of L squared, would be the absolute value of L. But if you just define L squared as the magnitude, we're saying the same thing with different notation. The problem is the textbook, and I double checked the textbook. I even emailed Dr. McDonald to ask. Maybe I didn't check enough other textbooks, but I couldn't find anywhere in the textbook where they used that L squared notation. And I've tried to make my notation consistent with the textbook. And again, I don't see, I see this spot where they say magnitude, but I don't see any place where they actually say this is capital L squared is equal to this thing. They always say if the angular momentum is represented by a vector of length L times L plus 1 to the 1/2, right? They always use the word magnitude. They never have that notation of L squared. Let me check something else. So it depends on whether you're talking about magnitude. Right, so it just depends on what that L squared without the hat on it means on the equation sheet. If that L squared without the hat means magnitude, then yeah, we've been saying the same thing. It's just, for me, usually when I think of something like, right, so like in the past, I won't do it with LZ, but in the past, when I've done things like px operator on some function, that gets me the px value times the function. So I could say, okay, that does make sense. That then you could say the L. Well, yeah. So that's where I think I got mixed up, because that would make me think if you're doing the L squared operator on a function, that would get you L squared times that function, which is why I thought it needed to be square root of L squared.
Okay.
I'm checking another textbook to see if they use this notation, just because I do want to figure out. I've been racking my brain about that, but I think it's just a notation difference.
So L squared without the hat is not magnitude?
So I always think of magnitude as like
Bless you.
I am going to disagree with.
Okay.
Ooh, I don't know if I want to say that on video. I'm not going to say that on video.
I'm pretty sure it's just the square and the.
So here's a way you can think about it that I think makes the most sense for how we're thinking about like what we should be writing down. And I'm sticking with this idea. In the textbook, it's this idea that magnitude equals the square root of L times L plus 1 h bar. Another way you can think about it is from that cone picture, right? And so if you look at that cone picture, which I'm going to do my best to draw a cone now. I think that's a pretty good cone. Right? This cone represents, that's my L vector. Right? That's my L vector. That's my L value. And that L value, that length across that edge, is going to be the square root of L times L plus 1 h bar. That's what that length is equal to.
And that's the magnitude of the.
So that would be the magnitude of the vector. Right? It's always a positive value. If the cone were flipped and pointing down, right? If the cone were down here because our m sub L value was negative, it would still be that magnitude. It would be that length of vector. And so to me, length of a vector would be like the absolute value of that L vector. And another way to write absolute value of L vector is the square root of a squared number. So that's where I was like, oh, I feel like there should be a square root on there. So on your equation sheet, the way it's written now, I found a little bit confusing because it's just saying magnitude is L squared. I'm going to put it in quotes, right? It's saying magnitude is L squared. But we need to take the square root of our eigenvalue to get the magnitude. Right? So it just becomes that idea of what are we calling the eigenvalue? And it's the square root of the eigenvalue will be the magnitude.
Can you explain how you got the values after the h bar, like the 0, 1, and negative 1?
Ah, yes. So from this definition here, right, that's my m sub L. That's my m sub L. That's my m sub L. I erased a little bit over there.
Isn't the... Okay, actually... Well, I guess, like... Wait, what was the LZ?
What's that?
What's the LZ operator?
So the LZ operator, we could go through the mathematics of all of it again.
M sub L.
Yeah.
Okay, and then the L hat is L...
So
plus 1.
L hat, not L hat squared.
I mean, L hat squared.
L hat squared
Is this definition of...
is going to be, L hat squared is going to be LX squared plus LY squared plus LZ squared. And again, we could go through the mathematics. If you remember, the LX operator was that thing that had cosines and cotangents and sines. And we were like, we never want to work with that if we can avoid it. And we said that's where spherical harmonic functions are really nice. Because if we're working with spherical harmonics, it's always just going to be that. And we never actually have to do the operation besides the few homework problems that say, prove it. Right now, I could have written another problem on the quiz and said, prove that you get m sub L for this function. And if I wanted you to prove that you get m sub L as an eigenvalue for that function, then you need to go to the definition of LZ is equal to I h bar negative I h bar d by d phi. And then you need to apply that to the actual function of whatever y20 is and prove that you get a 0 value out.
Oh, okay.
But since we already know that LZ operating on YLM just gives us the m sub L value out, we don't have to go through that proof again unless the problem specifically asks us to do that. Does that make sense?
Yeah, okay, I was just getting confused because, like, we're using a different operator here.
Right. So if we were, and I was trying to do a different operator, so you'd have to think about how you would, so like, just change that LZ to L squared and then use that definition of L squared. Like, I'm pretty much trying to do the problem with you without doing the exact problem. Is that close enough?
Can you repeat what you just said? To get m sub L, you have to use LZ to do, how do you get m?
So right now we're using this known quantity, right?
Oh,
Where
so-
we picked our YLMs to
Yeah.
be eigenfunctions
Okay, you're just
of
saying-
L squared and LZ.
Okay.
And since we know that they're eigenfunctions, and we already know the eigenvalues, LZ operating on any spherical harmonic is h bar m sub L,
Okay.
with the function coming back
Gotcha.
exactly the same.
Gotcha.
L squared operating on any function,
Mhm.
h bar squared L times L plus 1 times the same function back.
Okay.
So the question that we were asking, I think you came in while we were working on this one. So we asked a different question than what was on the quiz, and we said, is the psi function on the quiz an eigenfunction of LZ? So we applied LZ to the function we had that was the addition of these three things, and we said, okay, that's going to be LZ to each one, and we ended up with one of them disappearing because we got a times 0.
Mhm.
Since we got that times 0, it's not the same function anymore.
Okay.
So it's not an eigenfunction of LZ.
Okay, that makes sense.
Follow-up question for fun. Can you think of a way that we could force a function to be a linear combination that is an eigenfunction of LZ? Yeah,
If L is the same.
not L.
M sub L.
If the m sub L's are all the same number, you would make an eigenfunction of LZ. The other thing you can do is if the m sub L's are the same magnitude with the proper sign flips, that would also work. So, for example, if you didn't have that 2, 0 term there, and this one was negative, oh, does that work? Maybe that doesn't work. No, you're still going to have a sign flip. Yeah, so if the m sub L values were all the same, then it would still be an eigenvalue of LZ. Right, so this means when we want to start looking at making these, it could be plus or minus. When we want to start making these things, these linear combinations of orbitals, we can decide, do we want them to be eigenfunctions of L squared or LZ? And we can pick different functions to put together to make them eigenfunctions of whichever operator we want. Usually it's going to be eigenfunctions of L squared rather than LZ, which is part of why I did that on the quiz, because L squared is directly related to the Hamiltonian, so it would be in our energy space still, if that makes sense, right? We like to do things with, like, energy. You good? Question or just taking off? You're fine. You can just run.
You got your water bottle?
Oh, that's somebody else's water bottle that was left in class.
Alright, sweet. I'll see you later.
I think we all agreed it was Emma's. Oh, it's yours? Oh, there you go. Okay. Other questions about this? Yeah.
I have a question about 3B and like showing the orthogonal
Okay.
functions.
Anything further about 2? Good for now? Okay, 3B.
Because I got to like setting up the integrals and like combining the like complex conjugates and then
So what integral did you have?
I had one,
Oh,
Yeah.
this.
yeah, like 1 is equal to psi star psi, and I like plugged in the
Wait, for normalization for A or B?
for B.
For
So
B.
they're orthogonal.
So we're going to have 0 is
Or
equal
zero,
to, and I put a question mark over it because we're trying to prove this. We don't know if it's true. And we're going to have E. Did you do N or M first? So we have E to the IM phi, E to the negative IN phi, D phi. Put these together, and we're going to get integral of E to the I, M minus N phi, D phi.
That's what I had in the quiz.
I was just like, what is your strategy for solving it generically? Because I couldn't conceptualize it generically. I had to put numbers in.
Okay, so we've got 2 things we can show. The first thing that the quiz didn't ask about that I think is interesting, if m equals n, e to the 0, you're normalized. So if m equals n, normalization happens just naturally. The thing that becomes curious is, what happens if m is not equal to n? Now, question before I go further? Or?
Does it, like, isn't it normally, like, the first term is
Well, so this was on the functions we're given was
Functions to the theta, so we switch it.
right. We have e to the negative im phi star e to the negative I n phi.
Oh, because they're already negative.
So I chose the already negative function.
I see. Okay.
Could have picked the positive function, would have come out the same way. So the integral of this, there is a generic integral for this thing, and that's going to be a 1 over I m minus n e to the I m minus n phi from 0 to 2 pi.
So you just do like the standard thing, okay, how
Yeah.
do we integrate it? Oh, okay.
You just do the integral. You're right. So this integral, and this is the integral that's listed on the equation sheet in a funny way, where it has x to the n e to the ax, where in this case n is equal to 0, and so the integral becomes relatively easy. Now, analysis of this. If phi equals 0, it doesn't matter what m and n are, right? Phi equals 0, you're going to get 1. So, and then e to the I m minus n 2 pi. This one's weird.
Oh, e to the I m minus n plus
Times 2 pi.
1 times 2 pi.
Why 1?
You're adding the exponents when
So there's... Yeah?
when you add the exponents, you're multiplying them together. So you can just go up and
The e to the 2
The
pi,
e to
but it's like whatever the.
Oh,
sign-
yeah. So
oh,
this
plot
is...
e to the 2 pi.
So you can rewrite this as e to the I m minus n e to the 2 pi. Yeah?
That's what I'm writing it
Yeah. It took me a moment to keep track, but yeah, you're absolutely correct. And then we can do a quick check. If I do 2 times pi to the power of e. Whoa. No, that's not right.
Oh, but that's yeah.
That would be addition. That's not right. We've got to do something else.
Isn't it Euler's?
Yeah, we can do Euler's. Right? It's going to be a sine and a cosine.
It's because it's
Can
the
you-
cosine.
Can you write out what
Yeah.
Euler's is?
Yeah, can you,
Euler's.
like,
So if you haven't...
I don't think we learned it at all.
haven't?
No.
I remember briefly writing it down.
Oh,
yeah, like
so
it was very
important.
brief, but
What class would that be learned in? Like,
it
How
was a
far
4.
This-
And if you didn't
this
take
four-
Calc
No, we
4,
didn't learn
if you
Euler's
didn't,
before
if you
this.
didn't
This is the
take
first
Calc
time
4,
we've
you
This
wouldn't know
class,
that.
right?
Yeah, I've
Like
never
just
seen
in
that.
this class, e to the I theta. I'm okay if it's just in this class because there's only 2 things. There is a Taylor series expansion argument you can make to prove this, but we just kind of wrote it down. Cosine theta plus I sine theta.
So where would you put the m minus n in there? Does it go in?
It would go in with the theta, right? This whole thing becomes theta. Now, here's the part we have to, there's one extra thought piece that we have to keep in mind. M is an, is a constant. What kind of constant? Starts with an I. It's an integer. N is a, so we're going to have, no matter what m and n are, they're guaranteed to not be the same value, right? If they were the same value, you'd get 0 over 0, which would be weird, right? That's undefined. But as long as they're guaranteed to be different values, you're always going to get cosine of constant times 2 pi. You're going to get sine of constant times 2 pi.
Which equals 1.
Right? Sine of 2 pi, sine of 4 pi, 6 pi, 8 pi, 10 pi. Right? No matter what we pick for m and n, since they're going to be different values, that sine term will always drop out to 0. Cosine of 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, 200 pi. Still 1, right? No matter what we pick for our m and n values, it's always going to be some number times 2 pi, and we're always going to get that to be equal to 1. So you end up with 1 minus 1.
One minus I.
0.
1 plus 0? Oh, because wait, okay.
Right, so
1 minus I.
now I didn't mean to do this whole problem for you right now, but you're going to have 1 over I times m minus n times 1 minus 1.
I thought it was 0.
Why would it?
Is it good? Is it
You put
good?
that back all in there, that's what it was.
Oh, please. Wait,
Yeah.
What? Okay.
It's e to the 2 pi times, I'm just going to call it, let's call it a constant n prime, minus e to the 0.
Oh, yeah, okay, gotcha.
Right?
Yeah.
Now we were expecting to get 0, so if you got to this point where you're like, well, I know e to the 0 is equal to 1, e to the 2 pi better, e to the 2 pi times m n I better also be 1 if I'm expecting this to be 0. And the problem was show that this is true, so we kind of have a hunch that that's how it should work out.
On the
Question here
quiz,
back there.
I, instead of like doing it with like m and n, actually used values.
Uh-huh.
What is that like?
You get partial credit for that.
Okay.
Probably a lot of partial credit for that.
Okay.
Yeah, right, and using it with actual values makes things a little bit easier because then you can plug it into your calculator, right? If you know m is equal to 1, n is equal to 2, then you're good. I do like to see that kind of extra level of thinking of like, oh, it doesn't matter what I pick, I'm always going to get something times 2 pi. But still, lots of right ideas. Question back there. Yes, we can look at some other commutators.
I'm still confused on like where the 2 pi plus n prime.
Okay.
Where that comes from.
So, remember, so let's go ahead, let's do this a little bit slower. We're applying the limits of our integral. Right, so this thing doesn't have any phi in it, right? We did our integral of d phi from 0 to 2 pi. 0 to 2 pi. Right? So when I do this integral, I'm going to have 1 over I m minus n times the quantity of this thing at 2 pi minus this thing at 0. So I'm going to have e to the I
Yeah, exactly.
m minus n 2 pi minus e, oh, not negative I, e to the I m minus n times 0.
And then this is your. Oh, wait, no.
This one's easy to solve because it's e to the 0. That one's equal to 1. This one was the one where we had to do the Euler expansion where we were like, wait, what the heck is e to the I mn 2 pi? And we say, oh, that's going to be like a cosine term and a sine term where the sine term is always 0 and the cosine term is always 1. Because we know m minus n is equal to an integer, which I called n prime, right? Some integer value. And cosine of n prime times 2 pi.
Yeah, but this is your constant. N minus n is the constant that's in pi. So it's essentially just like
Where's the I though?
That's where the Euler expansion comes in, which was the part I just wrote down. And this is, I'll write it down here. Right, and this Euler formula is something that we should all have in our heads. This is really important. E to the I theta is equal to cosine theta plus I sine theta.
So if you did the Taylor series expansion or the expansion, you'd get cosine of n prime times 2 pi plus I sine n prime 2 pi.
Yeah, and then this cancels out with like one of these. Because of chain rule.
Okay, and this is still times 1 over I m minus n.
Yes. But that one over I m minus n part
Wouldn't you just
doesn't matter.
get 1 minus 0?
1 minus 0 or 1 minus.
Oh, you get 1 minus 0 minus 1.
Yes.
Okay, yeah.
You get 1 minus 0 minus 1.
Okay.
A girl saw this.
Which means you're going to have that 1 over I m minus n times 0.
Okay.
Which means it's equal to 0. It's orthogonal for any m not equal to n.
For the negative case where it's e negative I theta, it's cosine theta minus I sine theta.
Wait, for which? Oh yeah, if it's e to the I. Yeah, because that's essentially take and the easy way to remember. Easy way. The easy way to remember that is complex conjugate. Take the complex conjugate of both sides. That becomes negative. That becomes negative. The other way you can think about it is cosine negative theta and sine negative theta. Cosine negative theta is cosine again. Sine of negative theta is negative sine of the theta.
Oh, because then this would.
I just like every time I like Googled it, I wasn't sure if it was actually correct. So
Yeah.
I wanted to confirm that it was actually
So,
right and I wasn't just using it.
Complex conjugate of both sides is the way that I remember it.
Okay, I see.
Okay. Are we happy with that one for now? Happy might be the wrong word. Are we done thinking about that one for now?
Yeah.
Okay. Are there any other questions about the makeup, or are we ready to move on? Yeah.
Can we go with the
Oh, right, the commutator. Now, I want to do a different commutator than the one that's there, and I didn't bring my book that has a lot of great examples to campus today. So give me just a moment. I'm going to erase the. Actually, I'll just erase this first part. I'll leave the rest of this up while I try to find a good example of a commutator problem to do for you. Because we did some in class, and there's one that I really want to do that I think is going to be like such a mess to do, but I think it's worth doing. You actually already did it if you're following along with the homework. It's the LX, LY to get LZ.
Oh.
Should I try that one?
It wouldn't hurt.
It could hurt. So let me see if I can find, it's a doozy, to put it mildly. I would also love to do it with the raising and lowering operators, which are really, we didn't even learn about raising and lowering operators. They are some of my favorite things. But it's just time and time and time. The raising and lowering operators are these things that can be used to generate harmonic oscillators by just applying these operators. They're called the ladder operators, not harmonic oscillators, the circle harmonics. And they're really cool. But let me see here. Maybe I need to look in our textbook to find what I'm looking for. Oh no, here we go. Oh, cool. They've got a whole. So this textbook has a whole walkthrough of this commutator relationship. It just takes a page and a half. Okay. So let's go ahead. I'm going to do a different commutator that you'll notice is really closely related to the commutator that's on the quiz, but not exactly the same. And the one that I'm going to do on the board is actually more complicated than the commutator on the quiz. But let's take a look at it. And the one that I want to do is one that's really relevant to something we wrote down when we were looking at angular momentum. And it's the commutator of Lx with Ly. Right, this commutator is a bit of a hassle. Now, one of the things we have to do is we have to apply this to some test function. Right, I can write down that this is going to be Lx hat, Ly hat, minus Ly hat, Lx hat. But that doesn't really mean anything unless I'm applying these operations to a function. So we usually write this down as Lx commutator with Ly commutator, on some test function that's going to depend on x and y. That's going to be Lx, Ly on the function minus Ly, Lx on the function. Whoop, that's not how you draw that. Where when we think about this operation, this one says, hey, I have to operate Lx on the function before I operate Ly. And this one says I have to operate Ly on the function before I operate Lx. There's an order to the operations. We can't just change, we can't just move them around. Sometimes we get lucky and we can if it's just like multiply by 2. We know those commute from our arithmetic days. But since these could have derivatives and different things inside of them, we might end up with these very order-dependent phenomena. So let me go ahead and write down the definition of Lx and Ly. I'm going to do this in x, y, z coordinates rather than r, theta, phi coordinates because it's a little bit more straightforward. Is that the bell? Jeez. Okay. After this one, I need to eat before my class at 4 o'clock. I'll answer a couple other questions. If there's a couple quick coding questions, I'll do that. But I have to eat before I have class at 4 o'clock or I'm going to fall apart.
Can we get our quizzes back? Like
After these are turned in. I'll hand them back on Thursday after this is turned in. And it's important, I did have a typo in somebody's grade on top of the off shift that I fixed already. So it's important to check those grades off of what's posted in Canvas.
So they're correct now?
It was one person had a typo.
Okay.
So they should be correct now, but then there was one additional typo for one student.
Okay, gotcha.
Which I gave them a 28 instead of a different score. I was off by a digit. Okay, so we can define Lx. If I'm just doing it in the x, y, z coordinate system, this is going to be IH bar y d by dz minus z d by dy. And Ly operator is IH bar negative, okay, I thought I was missing a negative there. Negative IH bar z by d dx, z d dx minus x d by dz. So my function is going to be a function of x, y, and z. And I'm going to see what I get out when I do these operations. And this is something that is going to take me, I probably shouldn't do this one. But let's go ahead and first start with just calculating Lx on this function. Lx, oof. And to be clear, I'm going to just go ahead and factor out an IH bar from all of these because I'm going to have a negative h bar squared and a negative h bar squared. I'm just going to factor that out. And I'm just going to focus on the thing that's doing the operations, not the constant. So if I'm doing Lx on this, I'm going to have y times f d by d. I don't think I can use my shortcut for this. Of f minus z d by dy of f. Then I have to take that whole thing, and now I have to apply Ly to this. So that's going to be, oh, geez Louise. Okay, so that's going to be z d by dx minus x d by dz operating on y. Again, I keep wanting to use a shortcut, but because I've got multiple dimensions, I can't. df dz minus z df dy. So I'm going to have to FOIL this through. Now, this isn't going to be so bad. So I have to FOIL this through. This is kind of bad. So I have to FOIL this chunk through to both pieces. And then I have to FOIL this chunk through to whatever pieces to both pieces. So I'm going to end up with 4 different terms here. Why did I pick this one? Okay, so let's just go ahead and do this part to both. This first term is not so bad. That's going to be negative xy d squared dz squared of my function. Right, because the z isn't going to affect that, but it's going to affect that. Minus Here I have to do the product rule. Derivative of the first times the second, plus the derivative of the first times the derivative of the first is just this. So this is going to be, okay. Ooh. Okay, I got to be careful. Negative, this is going to be plus x times, apply the product rule, df dy, derivative of the first times the second, plus, now this is where it gets weird, df squared dz dy. Have you seen this notation before? This is like doing two derivatives at once. Right, so d by dz squared, we're used to that. That's like d by dz, d by dz. This one, it's d by dz, d by dy. So I'm just trying to put it all together into one thing. But I end up with that weird chunk down there that I really hope cancels. That's the first term. Oh wait, no, that's the first term. This is the second term. Okay. Now I have to do that same thing with this dx operator, which is going to be much easier because notice that side doesn't have any x's in it. So it's going to be a little bit easier, but I'm going to get two other terms over here. It's going to be zy d by d. And notice I'm keeping the order of these. The dx dz order, I have to maintain that order there. So that is this term. And then I've got one more term. I can't even fit in there. Let me give myself a little bit more space. It's going to be, this was zy df dx dz minus z squared.
Why isn't it in it d squared?
Say again?
Okay, never mind. You got it.
Typo. I just caught it. That all was from this term. Now we got to do the same thing with this term. Again, the one on the quiz was easier than this. I'm just showing you the process of how you'd have to. It's a lot of bookkeeping. It's a lot of keeping track of things. So now I have to repeat that process with this one. I'm going to get 4 different terms for this. And I have to be really careful when I do this. I'm going to flip colors to try and make it so I can do this and keep track. And I'm going to line it up underneath this one and hope that things cancel out. I'm really hoping things cancel out because otherwise this is going to be an enormous mess. So Ly on F is going to be z d by dx of f minus x d by dz of f. Then, and again, I'm switching colors to try and make it so I can tell the difference. Now I have to do Lx on that, so that's going to be y d dz minus z d dy on z d dx of f minus x d dz of f. Wow. Okay. Same thing. I'm expecting you to get a lot of terms. This one is going to be the easier one. So this dy, you notice in this chunk, I've got no y values. So this thing is going to be easier. So I'm just going to go ahead. I'm now looking for places where things are going to match up, and I think I'm going to get myself in trouble trying to do that. So actually, no, I'm not. I get a negative z squared. So if I look at this term, so if I do this one with this one, I get z squared dy dx of f. And then if I look at this term, I get, that's a zx term. I don't have a zx term. I was hoping I'd have a zx term. Plus zx d dy dz of f. Okay, so those were the two easy terms. Now I have to do the two more difficult terms. It's going to be this one and this one. This one is going to be easier. That's going to be a negative.
They should both be squared now.
Yeah, sorry. Thank you. Okay, so one of my terms, again, I didn't line things up as nicely as I would have liked to. One of my terms is going to be easy. That's going to be a negative xy d by dz squared. Oh, look at that. Okay. That one's easy. And now for this first one, here, I'll do it up here. For this one, chain rule, or product rule. Right, so this one, I'm going to have y times derivative of the first times the second is going to be d dx of f plus first times the second, which is going to be a d dz dx of f. Does this simplify? Oh, I think it does. Okay. Okay, hold on. So here's what I'm noticing some things. I'm looking for something in particular. Question.
I still have a question about whether the negative would be distributed to each.
This negative? That one?
Yes.
Yeah. So this whole thing in blue has a negative sign on it, which is going to make things cancel out. So these two terms that are the same, this xy d by dz squared, that thing cancels out. I'm looking for other things that are going to cancel out, so I'm looking for a zy. I'm going to FOIL these two things to get them. So I'm going to have a y df dx, and I'm going to have, and I'm writing this big at the bottom on purpose because I know what I'm looking for, and I'm going to have a yz df dz dx. Okay. Looking for other things that cancel. Do I have a zy? I've got a zy and a yz. Now, I said earlier I was keeping track of this order, but since f is just a function of x, y, z, the order of derivative in which you take a function, that commutes. Derivative of x, derivative of y, that commutes. So this zy term and this yz term, those cancel out. Did that make sense?
I got lost when you did I don't understand how you foiled out everything in green.
Everything in green. Okay, so I did the back term first because it was going to be easier. So I did z d by dy. That got me this this z squared term. Then I did zx, and that gives me the positive term here. Then I did the yz. That's this product rule here. And then I've got my yx, which is this term. Yx. Oh yeah, that's this term here. So I kind of did it in a weird order is the problem. Do you see it coming?
So
Yeah, I see what
the order doesn't matter when it's
so satisfying.
in front of the.
So once
Because
we
it's y. I think
this
it's
in
the
an
y
example.
negative x because it's in the order that it is. It's y negative x. So making it negative x y flipped me.
Okay, so multiplication of numbers.
Yeah.
Like once it's x times y and y times x do commute. Right? So that part commutes and that's okay. So I probably should have written that as yx just to be consistent. Same thing here. Derivative of x, then derivative of y. That commutes on a single function. If it's just derivative in series, like derivative and derivative, that commutes as well. That's what allows me to cancel out this zy and this yz term, because yz, zy, that multiplication commutes, this derivative commutes, so I can change the order. That term cancels out. This xy and this xy term, that cancels out. Now, they're both negative, but remember there's a negative outside of this entire blue
So
part.
that y df dx is in front of everything else.
No, this I put separate on purpose. This is added to everything else. Yeah, so this should be here. This should be added in from this part. So this should be like plus. Right, that's just added and I just ran out of space. I'm going to cancel out a couple more things. I got my z squared dx dy. That cancels out. My zx. Did I mess up someplace? I did. There's supposed to be a z out front here. I dropped my z, right? Because chain rule or product rule.
So the commutative problem on the quiz, it's a lot simpler.
It's a lot simpler than
this,
this.
right?
But this is like one of the most complicated
Yeah.
commutative problems I could do.
Cause the operator.
But it comes out really cool.
Yeah.
Right? So we end up with y d by dx and negative x d by dy.
That's the answer.
This is the answer. Which happens to be LZ. Ta-da. So LX and LY commute to give LZ, and we already knew that was coming, right? This is, if you remember in class, I just told you these commutation relations of LX and LY, and I didn't prove it. There's the proof for you. And it's just a lot of keeping track of things that commute. The things that I wanted to demonstrate was really that foiling of derivatives, which I saw a lot of people kind of doing weird things with that, and the necessity of applying the product rule as you do. I saw a lot of people who were just going from here, and they were just calling this like dz squared xy, and then they were calling this dxz, like they were essentially skipping the chain rule parts of it. And that creates, or product rule parts of it, and that creates incorrect math. So it was showing this foiling out and then showing like how things eventually end up, like most cases, they end up simplifying pretty well.
Yeah.
And again, this is one of the most complicated commutation problems I've ever done, like in my life. But it works out really nicely, and once you see how it works out, you're like, cool, it just does a rotation. I'm going to go ahead and stop recording. And again, the one on the quiz is easier than this, but there is a lot of keeping track of that foiling you have to do.
Right.
Okay, I'm going to stop recording. I'll answer a couple other quick coding questions, but I do need to get my lunch and eat before my next class, and probably figure out what I'm doing in my next class.